programming engineers. Welcome back once more to this drives course. So today I'm going to be teaching you all about a very important topic as far as drives goes. And this is a topic which is not always talked about. However, we really do need to understand these types of controls better in our frequency variators. All right, now what are we talking about? What are they about? What are they for? There are three types. The first type is volts hertz. So volts hertz controls. Our second control is vector control, or the FOC, which is field-oriented control, or sensorless and vector control, more commonly known as sensorless. And a different type of control is the direct torque control, the DTC. Now, what are each of these for? We, as programmers, as drives technician engineers, we need to know what type of application is the one that we're going to control. What type of application is it? Is it a conveyor belt, a common conveyor belt? And that conveyor belt, does it actually need torque or does it not need torque? And if so, should it be constant or is it going to be changing? Now, these questions are very important. They're pretty important that we keep in mind at the moment when we design our different control. So all the drives have these types of control, even though we don't know at the moment when we remove our drive, connect it and power it on, then it has a different defined or a different set type of control. What type? Volts hertz. Now what does this do? So to understand this, we need to analyze through its advantages, its disadvantages, and its application types. For example, let's look at the first system. Our first control, volts hertz. Now what do we do here? Well, internally, our drive, and I'm going to go in the most specific way possible so that we all understand without overcomplicating. For our formula part, no, that's actually already done by our drive. We're not going to calculate that. So then what does it do? It generates the control type by modifying every variable between volts and hertz. Both of them are completely modifiable. Now each one of them, if I modify my voltage part, my frequency part, it's also going to be affected. It's going to play around with these variables so that we can control the voltage. And actually what the drive does is modify the voltage so that it can control the velocity in a more efficient way. Okay, it generally doesn't need any tuning, generally. However, we can tune it. Okay, they can control many motors at one time with only one drive. Okay, so this is incredible. This is something very good that already has this type of control. Now you may say, well, Rodrigo, how am I going to control this? Well, they're going to be controlled if they don't need to start and stop independently. For example, if we have a fan system through our plant, and we wish to start with all ventilators at the same time. So we connect this in parallel. Through our engine output, we connect our motor, at least the ones that we're going to use. But since there aren't many variables to control, which means it's totally focused on the voltage variable and the hertz variable or the frequency, then this is a not so specific control. Let's say it's not a control that we need to be calculating for the gains or calculating a different type of data or variables, because we only need volts and hertz. That's it. Or at least their own variables that we want to try to control. So it makes this efficient at the moment of controlling its own velocity by controlling not by controlling position nor torque. So the voltage is being controlled internally. The drive, depending on where you're going to command it as velocity, then that is going to respect that velocity instead of modifying that voltage. Okay? Now, what I was saying was, we can control many devices at the same time, many motors, with one only drive, just as long as we connect it in parallel. Okay? No series. If we analyze this, they're going to burn out because we're going to be connecting all the phases. So, no, this is parallel. Now, the best thing is that this is basic configuration, for example, with much simpler applications. Now, its disadvantages, if you have a pretty large load, it's going to take her some time to move it. Okay, now that's the disadvantage. The torque part is almost not touched because it centers around the frequency variable. So if you use a commanded speed and without any feedback, which means that this is an open loop, it's not controlled efficiently. At least if we need to use more variables. Now, what I'm trying to say is, when are we going to use volts hertz? When these are easier applications, and specifically only for speed. Okay? So therefore, its applications are centrifuge pumps and industrial fans. We're not really interested in the torque. So all we want is for it to start, and from there, we can probably control all the velocity. And from there, there's no additional using the fans. Or if we already have calculated the liquid for our pump, and we know its limit, then if it works, the only thing I'm going to do is decrease the speed, and that's it. So these are very simple applications. Now, what's next? Sensorless vector control, the famous UVC. So advantages, we can control more variables between them, and what's most important, the position part. Remember that if this is for position, we're going to mess with motion control, but also for easier applications. For example, if you took the course for a complete PLC course for Alan Bradley, I know you're going to remember a very particular exercise. And with that, we won the project and we showed it to you guys. Okay, now that project was our very famous labeler. Okay, our labeler project. Now, those labelers, I never did it with any type of servo drive. I did not use motion because it was also overly excessive if I used my motion control. Now, what else do we need? One drive. Now, what do we also install? We generally connect an encoder. Now, that encoder helped me in getting the position, which was for the labeler. And regarding that information, then the drive internally is going to run its calculations so that they know when and how to stop. So it's basically this. This type of control is generally for torque applications, yes. But is this a larger torque or a smaller torque? But also I need something very basic. But this is only because we do not need an external sensor. But be careful, our drive uses our voltage, actually the current between the phases, and it's not running the calculations to try to get a better control. So we don't need an external sensor, but based on the current that is being internally done and based on the commanded, then in this case am I going to adjust its ramps to adjust their movements. Now it allows for better tuning. Yes, it does. For this type of applications. Okay, so for this type of applications, we need to improvise. Especially because of its composition. Remember that, guys. So as an advantage, we could definitely get some continuity errors if we're not really, that's going to be on our drives. So torque means larger current, and if we ask for a larger current, then there's going to be an internal temperature, and that internal temperature over our drive may damage our motor. Okay, because our drive is going to start sending out current to try to compensate over the torque. Okay, do you remember when I told you about the motor reducers? Well, that's what I said about the drives being very complicated to increase our torque. But we internally, with this type of control, it's all about compensating by removing, for example, our velocity. But we need to select this type of torque for the control type. If we have selected here our volts hertz and we decrease its speed, then the torque is not going to increase. And it's going to try to compensate if we have that control type SVC installed. And then internally, you can move around your gains, and you can compensate for the torque that is missing. But still, it tries to be a little bit more precise. Now, since this is compensating the torque or the comprehension, then which one is being more affected? So it can control one button at a time, one motor at a time. So it's not going to be able to control everything at the same time. So you guys need to be very careful with this. Now, applications, these are very simple applications, very, very simple position applications. And if we wish for something a little bit more complete, don't overcomplicate things and buy a servo drive. But these are very easy. And you'll see that you basically don't need that much precision. But not as exact as the motion part, where we need this type of control on your drives. Now, precision applications, what I was telling you about. This is logical, obviously, guys, because let's analyze this. Generally, for our drives and servo drives, for our motion part or frequency variators, we use three variables: velocity, torque, current actually, and position. Now, what are we going to get here? Velocity. So therefore, if we wish to control our velocity, our other two variables are affected by this, which are actually torque, because here it doesn't have as much. Precision, we actually have no precision or position at all. And so therefore, the only variable that is victorious here is speed. What do we need here? We need a much larger position or preposition. So therefore, the torque variable is going to be affected. And it's actually still compensated by women, but it's still activated. So this is what I was saying, that it decreases. And the velocity is definitely the one that is most affected by it, because it's being carried out with a larger scale, larger speed. Now the other control type, that's where we try to control our torque. So basically, if in a mine there was a conveyor belt for ramps, there's let's say for example, there's an enormous amount. So we need to control our variables, especially torque. So we are allowed, of course we are, for better tuning, a continuous torque. Okay, guys? Now, disadvantages, we might get larger temperature through our motor, which is the same thing as our sensorless. So our sensorless has less speeds, but it also has better control over it. Now, this is quote unquote, guys. There's a quote unquote control, an adequate control, but it's still at a minimum level. Okay, so we'd sacrifice our speed. Now, there's no position here. So maybe it has a different simulation with the sensor control device, because that's why this is low. Now, why do you think you get better velocity or speed control in this type of controls? Because here we're not using anything precision. We remove this. And since we don't need this, we compensate with a little bit more speed. Okay? So we can control one motor at a time. Applications? Well, just the ones that we need for linear torque. For example, this conveyor belt, which is huge, and that over the conveyor belt, we're going to have handheld or any devices, because it needs continuous torque. So with this, we're done looking at all three different types of controls. Okay, we're not making this up. These are all the drives. They're all the same. So before I have this, or before you have this, you're going to have this type of motion, this type of control. Now also, a very important data, the other type of control is being used for the permanent motor damage, magnets. Now, do you remember that some drives have this characteristics for permanent motors and magnets? Well, generally, if you guys are going to install this and you need a larger for more permanent house, then you need to select that control. So maybe you would say, well, why does he want either bigger torque or bigger precision? So precisely, that's why we use our different torque, by talking about frequency variators. So motion is very similar, but it changes many things. It's something a bit more different. And for you guys, if you already took my motion course, that's where you're going to get this. So with this, we're going to get all the different types of control. And you guys, at the moment when selecting the type of control, it's because you already have in mind the application is the one that you're going to need. Okay? Okay? Now, excellent then. Having said this, we're going to finish with this class and we're going to move on to our next topic. Big hug, guys, and thank you very much for your time, guys. If any questions, I'm right here.